Today, we are going to start on chapter 4 of this book, Multi-Agent Reinforcement Learning. And for this session, we're going to cover solution concepts for games, which is our first step into really how these problems are different from traditional reinforcement learning. And really the idea of having a game and a game model, um, as opposed to just ordinary states, is what distinguishes this stuff. So, um, given that we have these game models, we're going to define, end up what normal form games are and stochastic games, etc. Um, and end up introducing this solution concept, the most probably famous of which is the Nash equilibrium. But even prior to this, we're going to start with a simpler example. So the question we have to answer for these is how an agent, like what does it mean to act optimally for multiple agents? And now when we have a single agent system, like we typically have with RL, there was a pretty straightforward answer to this question, which is we're trying to maximize the reward that the agent gets. Now, if we have a multi-agent system, now each agent in general is going to get a unique reward. And we can no longer just simply say, well, we want to maximize the reward, except in the case of a certain type of game where all the rewards are the same for all agents, like they all share a reward. And that case can actually be reduced to just the single agent problem. So it doesn't really pose anything new. But in a multi-agent system where the agents can have, opposing rewards, then we have to consider, what kind of reward will all the agents get as a result of the joint policy. And by the joint policy, we now have a policy across all of the agents in the problem. At the beginning here, we just have some notation to get through. And this book, I would say, like, there's a lot of notation in this book that is somewhat, I guess there's a lot of superscripts and subscripts that can get confusing. But the authors of the book do provide this section. Um, wait, where is it? Notation section. Yeah, here. So you can see. So at the beginning of the book, if you want, to look at it, there is a summary of notation here. And some of it's just basic stuff like probability distributions. But this is the notation that really relates specifically to the game models. So we have the agents. We're going to use subscripts to denote, individual agents. And then, this is from more traditional reinforcement learning. We have the state space. But now there's this additional notation we have to worry about, which is for observations. And the reason why we have this is because when the agents are observing the game, we want the ability to control whether they can see all the information about the other agents and all the aspects of the game state. And if there's complete information, then the observation function can just provide all the information. But in general, it's going to be a subset of that information. So we have this. So when you see in the future, these sorts of notations, now the reward function also in traditional reinforcement learning, we get a reward value when there are state transitions. But in the multi-agent problem, now for a game, the reward function is not going to provide a separate reward for all of the agents. And that also is going to depend on all of the actions of all the agents in general. So it's no longer just going to be this simple function on every step. There's this whole, matrix of rewards that we can get. So here, let's go back to here. So now instead of a single policy, we have, the idea of a joint policy where the joint policy is just a set of policies for all of the n agents. And then we can look at the probability of a joint action, which is just the product of all of these joint policies. Here, H, I believe. Let's see if we go back here. So yeah, here H is now, if we look at the notation, the set of histories. And this is because in general for the multi-agent problem, It's not just the current state. Now, this is also something that is different from traditional reinforcement learning. Usually, only the current state matters. However, in the multi-agent problem, um, for repeating problems that go on for a long period of time, the agents may also have to react to the behavior of other agents, which they don't know ahead of time. They may have to learn what that behavior is. So we actually need this history function because this will include the history of observations from other agents. And that's not like part of the game itself, like in typical reinforcement learning. Now, if the other agent's behavior was completely fixed, then that would sort of be part of the environment. When we talk about single agent RL, usually we have a case like that, where even if we have other agents we're worried about, we would just fix them in place, consider them to be part of the environment, and then try to optimize the behavior of one agent against all that. But that is very different from simultaneously, learning optimal behavior for all the agents. Yeah, this definition. So if we take this product here, yeah, this assumes that all these probabilities are independent, so we don't have to look at the correlations between them. Yeah, so here's what I mentioned already. This is the history of the state's observations and actions going back into the past, and it includes, yeah, the states up to this point, and then the current state and current observation is also part of the history. But what's included here in the past is also the joint action of the history going back in time. So obviously we don't know the joint action at time t because that hasn't happened yet, right? That'll be included. Whatever action the current agent chooses will be included in the joint action. Okay, so yeah, we have these functions. Now, when we talk about the performance of an agent or what we're trying to optimize, just like in typical reinforcement learning, we have the expected return, which is going to be sort of the discounted sum of rewards for that agent. But in this case, this is looking at the probability of all of the histories going forward. Like it's because the policy in general is going to depend on the full history. We can't just look at all of the future state transitions that could happen like we would in normal reinforcement learning. We have to consider this whole probability of histories that it will experience, because these histories, including the behavior of other agents, will affect how the agent we care about responds to everything. But this is what I'm talking about, where the notation gets a little messy, because like these are transition functions, these are observation functions, and we have to sort of account for all of the probabilities of all of the histories, which includes all of the observation probability. So there's a lot of probabilities, but then in the end, what we care about is this discounted sum here. This looks a lot like what we have in single agent RL, where we just have the discounted return. But here, the return is just including a lot more possibilities, including the actions of all of the other agents. And yeah, we can, just like in ordinary RL, we can express this in a recursive relationship. Like here, we're writing it out where we're actually adding up all the probabilities. But here, we're writing it out recursively, where we only look at the observation from a single transition here, where we have, S and S prime. And because, actually, I just want to see here. So this is sort of laying the foundation for what we're going to eventually do when we have to track agent behavior over time. But when we first introduced this topic, we were actually just looking at single games. Actually, let me stick this back here. So we have these normal form games where we have the complexity of having multiple agents and the joint action, but we have the reward function, which tells us what reward each agent gets for the joint action. But the difference is here, the game stays the same over and over. Like this is just a single game that we could write down exactly what reward each agent gets for the joint action. So there's no history here. There's no like transitioning into different types of games. And this already really contains a lot of the math and complexity that we have to deal with. So for most of this chapter 4, we're just going to deal with this normal form game. We're not going to consider the part where we have repetition. And there's this diagram here I showed last time where we have n agents, but there's only one state here. And the one state is going to be this game as defined by the reward function. And here it's actually repeated, but we're going to actually first consider a case where it's not even repeated, where we just play the game once and we try to analyze what's going to happen in that case. So let me see here. So I think what I'm going to do here is now more focus on this notebook I made to explain some of the details of normal form games. And we can see where some of the complexity creeps in, even for a case this simple. So for these games, we have a finite set of agents from 1 to n, and a finite set of actions. And then the reward function is going to be a function of the joint action. So this means like, which action is taken by each agent. Okay, so in order to play this game, each agent selects a policy which assigns a probability to each of the actions that it could take. And so each of these probabilities, because this is a probability function, each of these will sum to 1. And then the agents sample their action according to these probabilities. So, and then after that, there will be a reward that is produced for all the agents, right? Based on this function. So the joint action will be this collection of all the actions selected by all the n agents. And then the joint policy is just going to be a list of all of these vectors of probabilities for each agent. Now, the first concept that we have, and I'm going to show a concrete example of a very small game so we can actually see what all these equations look like. Because right now there's just a bunch of subscripts and it's a little confusing. So we can think about this concept, which is the best response policy. And this concept is that, let's say that we take all of the other agents that are not I, right? So this pi subscript minus I is the notation we're going to use to describe the set of all of the policies for every other agent. Now, we can say a best response from the agent I, the one that we care about, is the one that maximizes the expected return for this agent when playing against all of the other agents. Okay, so pi I, right, is this collection of probabilities that the agent we care about can, set its policy. It can assign a probability to each of the actions that it can take. So the best response would be this pi I right here. This is something that can vary, right? We're taking the argmax over pi I. This pi negative I is fixed. So you can imagine just, without actually knowing how to do it efficiently, you can just look at all the different, possible policies that we could select from and optimize it so that we get the highest value. But this will be ultimately, a function in the space, in a space of dimension n, where n is the number of actions available to our agent I. Okay, but right now this doesn't really tell you anything about how to actually construct this. This is just about the concept that if all the other agents, if their behavior is already fixed in place, then we can look at that behavior and choose our policy that exploits that as best as possible. Okay, so it's in other words, it's just the best possible response we can make to the other agent's policies. Does that at least make sense as a concept, even if
wait, why are we considering all the other agents as fixed?
Well, because it allows us to define this concept. Like if we have to if we just have all the agents can do anything, then we're sort of lost. Like we don't know. But for now, we can at least say if the other agents are fixed, we can come up with a best response, right? Now, of course, we fix them in some arbitrary way. It might not actually represent anything. But the point of this is just that the concept exists that we could calculate a best response if we knew the behavior of the other agents.
Makes sense.
Right? Okay. So now to make things a little simpler, let's just consider 2-player games. So in a 2-player game, right, n is 2. So we only have 2 agents, and now we can represent the reward function as a 2x2 matrix, where here, like let's say I'm going to label the 2 players x and y. Okay, so this is r sub x, r sub y. This is the reward for this game for player x. This is the reward for player y. And I'm just using this notation where I have each element of the matrix and I have the superscript distinguishes whether it's for x or y. So what this means is like, this is the reward player x gets if x and y both select action 1. And, similarly for all of the others. So this means like after both players select their action, we can consult these matrices and then find out, what the joint reward is. Okay. And I'm just going to use the number to define the action. So like this 1 here just means, or this L just means this is the Lth action available to player X. In general, the 2 players could actually have a different set of actions from each other, which is why we're not just using the big A's here. But for most games, the set of actions could actually just be the same for both players. Okay, so now when we talk about the joint policy, we just have the 2 different probability vectors, right? So we're going to have all the different probabilities for x and y, and this and the joint policy will be the set of both of these together. And we can also talk about something like a pure policy, and that would be one where you can only select one action. Like if we set this at 1 and all zeros, this means that x is going to select action 1 with 100% probability, whereas this would mean action 2 with 100% probability. And if a policy is not pure, then it's a mixed policy, meaning it's stochastic. So there's some non-zero probability of selecting more than one action. Whereas a pure policy is a deterministic policy, meaning the action selection would always be the same. So does that make sense?
Yeah, the difference between the pure policy and mixed policy regarding the stochasticity of it makes sense.
Okay, great. Okay, so we've reduced now the game thing down to just 2-player game. So like if this was a 3-player game, then instead of being like a 2x2 matrix, this would be like this would be a 3-dimensional thing where we have 3 different indices for the action from the 3 different players, and as you go up, you just make this higher and higher dimension.
So essentially a tensor at that point, or some.
Yeah. I mean, you could whatever notation you want to use, but yeah, we just basically add more indices we have to keep track of. Okay, so now we're going to make it even simpler by talking about 2-player zero-sum games. Now, a zero-sum game is just a game where the reward matrix of x is always the negative of y's reward matrix. In other words, r sub x is just negative r sub y. Now that means we don't have to write down both anymore. So we can simplify our notation a bit by just writing down a single reward matrix where we're just going to take the first player and use those values. So if we care about the reward for the second player, right, we would just take the negative values of these. Okay, and then we can get rid of this superscript, and we can just have all of these. Okay, so now we're at a 2-player zero-sum games, and now we can talk about, I guess, the first real theorem that ever existed in game theory, which is the Minimax theorem. Now, before the Minimax theorem, well, actually, I believe that the Minimax theorem proves that this solution, which is defined here, exists in every 2-agent zero-sum game. So this was proven in 1944, but the proof is an existence proof. But really, what's important about it is the concept of what the solution is. And what it is that if we look at a given player, well, this is actually looking at both players. Now here, this is I and J, so instead of X and Y, which I think is a little confusing because they also use I and J for subscripts on the actions, like the action indices. So whatever. In this case, UI actually means the expected reward for the first player, and UJ is the expected reward for the second player. And there is a single Minimax solution for this game, which is defined by the fact that it will be shared between the 2 players. So the value is that from X is negative the value from Y. Right now, this always has to be the case just because it's a zero-sum game. So the reward values are always negative of each other. And then it obeys this other property, which is that if we look at the reward function for the player, the first player in this case, and we consider all of the policies that could be taken from either the X or the Y player. And if the second player is trying to minimize this value, and this value, remember, is the reward for the first player. So the second player will always try to minimize this because their reward is negative this. So minimizing this for them is the same as maximizing their reward, minimizing the first player's reward. And then the first player is trying to maximize the reward. And the idea is that if we change the order of this operation, so here, first we minimize this over all of the possible policies, and then the first player selects the maximum of that, versus first, for every fixed policy from the second player, the first player maximizes that, and then the second player chooses the minimum value out of all of those. That swapping this order here doesn't actually change the answer. And what that means is that this joint policy is the best response policy for each player against the other player. So both players are simultaneously making the best response to each other if this property holds. And like the problem is, in order to actually calculate this, right? Like if this is, let's say, like a function in 2 dimensions or something, we can go through and consider all the policies from X, right? And for each one of those, we can have the Y player minimize that. But I mean, there is an order here, right? We can't really do this simultaneously. We have to, first do this inner part and then the outer part. And the reason why, the fact that it doesn't matter which order we're doing is the proof that we are simultaneously, optimizing the best response for both. If this had a different result, right, then we wouldn't know which one it's like, sure, we might have found the best response to something, but it's not actually what the other player is going to do. It's something else. The fact that all these things match is what makes it a Minimax solution. And I think I do have, you can look this up, but this is some document from von Neumann where he came up with it. It's actually pretty long. It's like 30 pages or so. This actually might be from one of his books, but it ends up going through. And if you read this, like the notation is all pretty different, but he ends up like writing down a bunch of really complicated stuff and then eventually reducing it down to a very simple case. But this book, at least, does not provide a proof of this because it's not exactly the focus of this book to prove things like this. But I did find actually, yeah, actually, so in this document, there's this theorem actually that all of these things are equivalent to each other. And actually, I guess in the book, this definition. So really, like, there's sort of two aspects to the proof. One is showing how these things are equivalent, and the other is showing that for an arbitrary two-player zero-sum game, this solution actually exists. And I can put in the meeting description or something a link to this document at least. But this is showing actually John Nash, who the Nash equilibrium is named after. He has a proof of this theorem, which involves using some other, this Brouwer fixed point theorem. But I don't think we'll go into that now. I'm also, not familiar enough with the proof to really explain it. But you should just take for granted that this was proved a long time ago. The important thing is that this solution does exist for games like this. And then the question is, how do we actually find the solution? Because that's what we're interested in. So in order to look more closely at the solution, I am going to make the game even simpler than I already have. And we're going to look at the simplest possible case that we could have, which is two actions. So this is the most trivial game that you can have. A zero-sum game with two players and two actions. So now the reward matrix has 4 values in it. Okay. And this is for the 4 different combinations of actions, of joint actions that could be taken. Right. So we have 1, 1, 1, 2, 2, 1, 2, 2. This is just for each player taking that respective action. And then we can define the policies by just these vectors of 2 values. Right. So we have for player X, the probability of action 1 and the probability of action 2, and similarly for player Y. Now, right, we had this expression here. Now, what this means, this is the expected reward for player X, this U. So we actually have to write down what that is. And luckily, in this case, we can write down exactly what this expression is. And it is this. And there are 4 terms. Now, each term is the single reward that the X player will get when this happens. And this meaning both players take action 1. And then this is the joint probability of that happening. And this is, we're assuming here the policies are not correlated again, right? These are independent probabilities. So here, this product of probabilities is just, this is an expected value because we're taking all of the possible rewards that X could get, and we're doing a weighted sum of them by the probability, which is just, that is the definition of the expected value. Now, we can look back at this equation 4.11, and we can rewrite it using this notation, right? So this was expression 4.10. Now, if we rewrite it here, we have, right, this min and max, but now instead of just leaving it as the policy, I'm explicitly writing the 2 variables that make up the policy. Okay, so we have, right, like when we talk about minimizing this expression over the policy of player Y, we mean, selecting P1 and P2 for for y that achieves that minimum. And then in the parentheses here, this is just the actual expression for the reward. Now, on top of this, we know that these policies are probability distributions, right? So we can further simplify this by just only writing one of the probabilities, which is the probability for action 1. And then action 2 will just be 1 minus that. And then I'm just going to call P1x lowercase x. So this lowercase x will just mean the probability that agent x selects action 1. And similarly for y. Okay, so now this max min thing here, now we only have to do it over one variable, right, instead of two, because the value of the other is implied by the first one. So I have just gone and written this expression out, replacing, x, and this is 1 minus y, or sorry, so this, for this first expression, right, we have x, this becomes x and this becomes y, and every time there's a p2, that will just be 1 minus the corresponding x or y. And I've just grouped the terms a little bit here. This final expression here, I've just written where I've written one term, which is multiplied by y, and then these are multiplied by x. But the purpose of writing it like this is if we consider this inner expression here, right? This is the min over y. We can imagine that x is fixed, right? And then this is an expression of y, and these are just linear functions of y, right? It's just a times y plus b if we have this. Now, so if I create this reward matrix for this game, like here's an example of one, right? These are just the 4 different reward values. So then these are all of the lines inside of this minimization expression for different values of x, right? And in general, x will range from 0 to 1. So we have all these different expressions. And if I change this, we'll see these lines will change, right? There'll be like a collection of these lines. And in general, you could change any of these values and it will end up, changing this in different ways. But let's say, like, if we just look at one of these lines. So this is like, well, actually, I'll take one sort of in the middle. This is like x equals 0.56. So this inner expression here is saying, choose the value of y that minimizes this, which is going to be y equals 0, right? Now, if you go back and look at all these lines, because of the structure of this, and that this is linear, I'll redo the values to here. Where the value happens, like the min y, it's always going to be at one of these endpoints, right? Y equals 0 or 1. Like for these lines that slope upward, it's going to be y equals 0. But for these lines that slope downward, the minimum occurs at y equals 1. But that's it. There's not actually, we don't have to worry about any of the interior points. And then this outer expression means we take all of these. So we look at each one of these lines. We then pick either y equals 0 or 1, whichever one is the minimum. So then we have that value for each of these. And then we just pick the one that is the maximum value for x. So x is trying to pick the line here for which the smallest value on the line is the highest, which will end up being one of these lines, right, which kind of crosses in the middle where the value is just 0 everywhere, right? Because if we pick any other line, we can see that it's going to end up going below the axis here. So, now you wouldn't actually do this, right? Like in general, there's an infinite number of these x lines, but conceptually, the important part is that for each one, even though it looks like we have to minimize over y, we actually only have to check two values, right? 0 or 1. And that just comes out of the fact that of what this expression looks like, that it's just a linear expression in y. So does this make sense so far? And what, yeah. So what I'm showing, that this plot here, this heat map is actually showing, like in general, right? This function in here is a 2D function, right? It's a function over x and y. This heat map is just showing the actual function itself. And this line here and what's happening here is just the process of going through each of these fixed y's, and then along this path, choosing the minimum value, and then looking at what that value is everywhere. And that's what is happening here. This is showing the best value that x can achieve. Yeah, at this value of x. Like if x selects, 1, the problem is y, is going to end up selecting 0, which places the value at -1, right? And it's only at this intermediate value here that we can actually force a situation where y, whatever value y picks, it will end up having a value of 0. But you can see here, it actually ends up being this point in the heat map where if we select x here, we can see that as we go up and down, because of the color here, y is actually indifferent to its choice. Yeah, so that's like sort of conceptually what's happening is we're sort of going along through this heat map, and we're going along, and at each point we're seeing, what would y's response be if we were to select this value? And we know that y is going to pick a value like down here, so we need to end up going to a point along x where, regardless of what y does to sabotage us, it can't be, it's not the worst possible outcome. And that's in this middle point here. Now, if I change this again to like some other arbitrary game, we can see the point where this happens changes. But structurally, it's always going to be sort of a path along here vertically where all the values are the same. But we can see more details of how this works by doing a little more algebra. So I already mentioned that for this inner part, we can reduce this to just checking y is equal to 0 and y is equal to 1, right? We don't have to actually minimize over all of y. So first of all, I have replaced now this min over y. Now it's just the minimum of two expressions. The first expression is if we set y to 0, right? So this whole term gets zeroed out, and we're just left with this. The second expression is if we set y to 1, and then there's some cancellation that happens because this x term, if we pull in here, it ends up canceling at the r12 and the r22. So we're left with this expression. So now we have a max over x. And then inside of it, we have these two different lines. Now, these are now both two different functions of x, but we have to take the minimum between them. And that's what I'm showing here is both of these lines, right? So this represents the first expression in the minimum, and this is the second expression in the minimum. And if you imagine doing this, where if you go along x here, right, you say, well, which value are we going to pick? There's two possible ones. Well, the one we pick is the minimum between the two. So it's going to end up being this lower triangle here. And then we have to maximize that function. So now this function is going to get maximized right at the top of this triangle. right? But now as we change these values, we can see it's going to end up moving these lines around. But, it's always going to be two lines like this. And basically, as I change these four values, the lines can move anywhere, but they're still going to be lines. And considering we have to maximize this, there's something that we can sort of infer now about the solution. Like, let's say I actually want to find, like, the goal again is to find the value of x that maximizes this expression, where now this is going to be the minimum between these two lines. So the question is now, is there a pretty, simple way from this to do this maximization over x? Considering, I mean, this is sort of, right, this is like a piecewise function, right? We have two different pieces where it's going to transition from one to the other, where by this minimum operator. So I'll say, the answer in a minute or something, but I'm just wondering if it seems obvious to anyone what you would need to do to actually find this value of x that produces the maximum.
My first assumption was to find the intercept about within those two functions or something. Well, I might be wrong, but that's my assumption.
So for this case, right, this function we're maximizing is actually this lower triangle, right? If we take the minimum. So in this case, it appears the maximum is at the intersection point, right? So yes, that is correct for this case. But in general, like let's like take this case now. So now, but like now what do we do? Because the lines don't intersect.
I presume taking one of the points out that's with the line and the boundary of the problem. So either it would be probably where trace, so it would probably be a 1 or something.
So now the minimum is just represented by this blue line, right? This constraint is irrelevant because it has a higher value everywhere, and we have to take the minimum. But if we actually have a regular line, the maximum value is just going to be at one of the endpoints again, right? It's not going to be anywhere else. So from the structure of this problem, we actually only have to check 3 places where the solution could be, because it's either going to be at one of the extreme ends, right? X equals 0 or 1, or it's going to be at the intersection of the two lines. It's possible the lines won't actually intersect, anywhere, in which case we don't have to check that, or the intersect. In this case, the intersection actually happens at a point x is greater than 1, which we know is not going to work.
I guess in this simple case, could the entire system be rewritten in terms of a convex optimization function where it was like, the function given, conditions X, Y, and Z?
Yes.
Essentially.
It can be, yes, it can be written that way. But in this simple case, we can actually do everything by hand and kind of infer where we need to check for these extreme values. So, okay, we have to check these 3 things. Now, like the first 2 conditions are actually trivial. The only thing that requires some work is the intersection point, which itself is not too hard. Here I'm just setting the 2 expressions in the minimum equal to each other. Okay, we're just going to find where these two lines intersect. And then we can just solve for x. And it turns out x is this, so it's just a function of the 4 reward values. Yeah, so now we've reduced this whole, right, this general problem here, at least in this 2-player 2-action case, to now this problem, where we have to just check these 3 cases. So the x equals 0 case, this is the value, right? This is, I mean, x equals 0 means that we select action 2, right? So what we're doing here, this is the minimum of the 2 reward values we could get if we select action 2. And then similarly, this is if we select action 1. And then this is the mixed case, where it could be an intersection point. And here it's going to be the minimum between the value here if we plug in the intersection point. And actually, sorry, I need to rewrite this. You don't actually have to take the minimum here because these values will equal, right? These are the same value by the fact that it is the intersection point. Let's see. Okay. Yeah, there we go. So value should be the same for both because it's the point where the lines intersect. Okay. Yeah, so now we have a pretty, concise way of checking this. You could even do this by hand. And that is what is being done here, actually. So what I'm showing here is the function where I've set up the game. This is the reward matrix for the game. And then this is, at least for the X player, those 2 lines that we have to select the minimum between them, right? And here, you can also repeat this process for the Y player. It's just you have to write down the reward in terms of Y. And that's what's being shown on this plot is the 2 different, optimization functions for X and Y. And then the corresponding Minimax policy, which is just being represented here by the single value, which is the probability for each player of taking the first action. And here we can see like the policies don't necessarily have to match. Like here, there's this 0.71 and 0.57. And then this is showing the actual value for each player too. And what is true, because this is a Minimax solution, is that the values will mirror each other. One will be the negative of the other. And then as I change this matrix, like if I reset it to be the original one, then we can see this is a case where both policies match here. And then I can just change this around arbitrarily and you end up getting, I mean, it could end up being any kind of weird solution where both players could have a mixed policy, or one player could have a mixed policy and the other could have, like, here's a case where, oh no, that's not actually a case like that. But you could imagine, like, this whole thing is represents a large space, possible games. But, in principle, we can solve all of them. With this, at least in the 2-player case, we have this convenient way of directly checking each of these, and then whichever value is the highest. Of course, for here, we have to be careful and make sure that, right, the intersection point is not outside of 1, because that's a case where they in fact don't intersect at all, and we have to disregard that. But otherwise, we just have to check those 3 cases. So at least for the 2-player 2-action game, we can visualize this. Now, okay, so any questions about this solution?
You assume that the policies were not related to each other, but it seems to me that if a player knows the policies of the other player, they can adjust their own policies, in which case they wouldn't be non-correlated. Does that make sense?
I think what you're describing is only a factor for a repeated game where players would play over an extended period and get to observe the other player's behavior and possibly adjust it, right? But we're talking about non-repeated games.
Oh,
So the
okay.
players sit down and play. So we're assuming that information about how the other, so this is like, if you don't have that information about, what kind of agent you're dealing with, how it might, because then you're talking about, you might be willing to have low success in the game early in exchange for succeeding later on in the game. If you're assuming that policies can change over time. But in this case, we're assuming we don't have any information like that about the other players. This is just the best you can do, the best both players can do, just knowing about the game itself, right? Not like with this chance to repeat it over and over again.
Great,
Minimax
thanks.
theorem is the theorem which says that you don't actually need the policy of the other player in zero-sum two-player games in order to pick the best strategy for you. In other words, knowing the strategy will not help you if that other strategy is optimal.
Yeah, that's true. But again, like this is all for non-repeated games. Of course, like we could repeat the game, right, by playing it more than once. But when we talk about a repeated game, we talk about a situation where the policy could actually depend on the history of actions from the other players in the game state, and that could change things. I don't know if it actually changes anything in the zero-sum game situation, but it definitely can in general sum games, which are games in which the reward values don't actually sum to zero. Oh yeah, is there a way to tell from the equation output that the intersection is outside the bounds? So it's basically if this quantity is greater than 1 or less than 0, and you're asking, is there a way to know before you calculate this fraction if the intersection point, I don't know. If you have two lines and so, I mean, yeah, so you could check the value at x equals 0 of the two lines. So you could check if they see, like these two lines intersect, right? But they intersect outside of the bounds. So you could check in a simpler way, probably if they well, no, of course, yeah. I mean, you have to check if they're parallel. So if they're parallel, they don't intersect. You can check if they're parallel by only evaluating, right, the slope. So you compare the slopes. If the slopes are equal, which is R12 minus R22 and R11 minus R21, then you could ignore the intersection question. And then that's one like trick, I guess. I don't know if there's any other like shortcut to avoid checking this. But of course, in this case, it's a pretty small thing to check in the first place. So yeah, I mean, this is already reduced down quite a bit. There may be some other shortcuts. Okay. So then I just basically solve this exactly without any reference to some other, I mean, this is just basic algebra, right? And inferring things about linear functions. But remember, this is for 2 actions, 2 players. Now, what if we have 3 actions? So we have 3 actions. it's a little more complicated, and it turns out, we can't exactly write things down this conveniently and do all of this, right? Like this required a certain amount of reasoning with these lines and what points we actually have to check in the first place. But in the book, there's this claim. Now, again, like to actually prove that this is the case relies on looking more at the Minimax proof, you see? Because so far, all we did was we defined the Minimax solution. Right? Which, actually, where did I define it? Find it here, right? This is the property of the Minimax solution. Now, the claim in the book with these equations is that solving this optimization problem is equivalent to finding the Minimax solution. And we can see, obviously, this does not look like this, but there's some of the information we can infer. Like, for example, here, this constraint here, right, is looking at the return we get for x, right? See how this is for all j? What this is doing is saying, let's say that the second player selects action j. Then it is calculating what our expected return would be for the first player as a function of the policy of the first player. And then there's a constraint on this. Now, notice how there's no reference here to y, or to y sub ai, right? Just like when we ended up solving this, and I made the claim that we only have to look at the extreme values of y, like 0 and 1. It's the same thing in this linear programming problem, where we don't have to know anything about the policy of player y. All we have to do is check these constraints at the extreme values, where y is either 0 or 1. Now, this doesn't mean that the optimal policy for y is actually a pure policy. It may end up being, like in this, right, I showed a case here where both players had mixed policies. But in order to calculate the Minimax solution, we don't actually have to worry about that. We can just consider the constraint in terms of the pure policies that y could have. I mean, this constraint is kind of obvious. These two constraints are obvious. These ensure that the policy we solve for is a probability distribution. This one is a little less obvious, but it basically follows from some of the argument I made here. We only have to worry about the extreme values. And then the claim is that now this is a linear program with constraints that we can solve. I mean, a linear program is just an optimization problem where all the constraints and the objectives are linear in the variable that we are maximizing over. So broadly, this should be a linear program. However, if you look up a linear program, you find this definition, right? This is written in vector form. So it's find a vector x, right? X, these are the variables we're trying to find, that maximizes this. So this is the objective function. This is a linear function of x, where there's just weights. See, so this is just a weighted sum of x, subject to this is a set of constraints where A is a matrix. So we have as many constraints as we want, but we're going to have additional weighted sums of x, and then a constraint that weighted sum is less than or equal to some value b sub I. And then, all the x's are positive, all the values of x. We can write this without the vector notation like this, right? So we have a set of variables x where we're maximizing this weighted sum of x. We have these constraints, right? Where we have more weighted sums of x less than or equal to a set of values b, and then all the x's are positive. I mean, of course, a linear function, right? In calculus, when we optimize nonlinear functions because they have, local minima, and that's what we're trying to find. This is totally different. We have a linear function. There is no local minima. the only minima or maxima we get is because of the boundary of the constraints. So if you imagine that there are, let's say, two or n equals 2. So we have two variables, right? And then we have an objective function. The objective function, like we can have a plane, an XY plane that represents the values of the two variables. And then there is the objective function above that plane. The objective function is just going to be a plane in this 3D space. And then the boundary, these other constraints basically create some boundary in the XY plane that if we project up onto the objective function, we just want to know where on that boundary is the maximum. So in general, right, we would have to check all around the boundary for the maximum. But these boundary conditions, right, it's not like a smooth boundary, right? It's generally a boundary made of lines, of intersecting lines or planes, or in higher dimensions, hyperplanes. So we don't really want to check everything on the boundary. We want to sort of find a convenient way where we only have to check certain points on the boundary. And that is what happens when you use some technique from linear programming. So it's all glossed over here. It's like, okay, this is a linear program and you can solve it with a linear programming solver. It's like, okay, fine. Now, right, for the simple case with the two actions, we didn't have to use a linear solver program, right? We can actually analytically find out what these values are. But for the general problem, we do. So we write down a linear program. We have to write down the objective function, define the variables, and then write the constraints out. So now if you look at this, the claim is like, okay, this is a linear program. But it's not exactly what you want with a linear program. I mean, first of all, this is saying minimize this. Notice that the objective function here isn't even written out, right? Like there is no objective function. This is just like minimize this is something. And then it appears in the constraints. So whatever we're minimizing is also one of the constraints, which is not typically what happens in a linear program. So this is kind of unrestricted. And then, this is an equality condition. Also, not typically what you see in a linear program, right? There's no equality condition here. So this is not, we have to do something to this, right? To turn it into a linear program. But I don't know if anyone else read this or is familiar with linear optimization, but like, do people see what I'm saying? How like this alone, the way it's written at least, is not exactly in the form of a linear program.
Yes, but it can be easily written in that form, right? So one of your variables is uj star, and you maximize minus uj star, and you solve the equation everything equal to 1 to eliminate one of the x's.
Okay, I think I understood part of what you were saying. Well, again, like the fact this is minimum instead of maximum is not really the problem.
Well,
for me,
there
anyway.
was, some ways, to rewrite this. I just don't remember very well from, convex optimization, but.
Yeah, well, let's actually look at this and see how we would have to rewrite it to do this. So yes, we can convert this into a linear program. But I would say the transformation we have to do is not, I mean, it is somewhat insightful what you have to do. And there's actually a few other wrinkles you have to deal with. So we're going to do a change of variables on this. Okay, and the change of variables we do is actually going to create the objective function, which doesn't really exist here. So we can consider a new set of variables where we're going to take this and leave it. I mean, we're going to say this is the thing we're optimizing, but we're going to actually divide xa by whatever this value is. And we're going to take a new set of variables v that are x divided by this And then, you know, we know that all the x's are positive. Now, what if we take the sum of these v's? Okay. We take the sum of these v's, they all have the same denominator, right? And the numerator is just a sum over x. So very trivially, this sum is just the inverse of the actual value that we're optimizing, that we would like to optimize, the inverse of this. Which we're going to actually call this, we're going to refer to this uj star as the game value. The game value is just the reward that the first player gets under the Minimax solution. And the sum of v is the inverse of that. So now let's just say for now that the game value is positive. We don't actually know that, but let's assume it's positive. It actually turns out that this part of it will be the same if it's positive or negative. So originally we want to minimize u sub j. So if we write this down, then minimizing u sub j is actually equivalent to maximizing the sum of these, where we're summing them with weights of 1. Okay, so now we can write down our new linear program, which is we want to find the set of variables v that maximize the sum of the v's subject to these new constraints, where now we can divide both sides of this by u sub j, of course, assuming u sub j is positive, which we don't know, but let's just say it's positive. Then we have this new constraint, this is less than 1. And then because the u sub j is positive, and these are positive, we still have this old constraint that all the new variables are positive. Okay, so does this change of variables make sense? Yeah, I mean, now we actually have an objective function, which is a function of the original thing we were trying to minimize. So now the only thing we have to worry about here is like, how do we ensure that the game value is positive? Right, because if we have a general zero sum game, well, one thing we can do is we can look at the reward function and we can pick out the minimum value, and we can just define a new game where the rewards are this minus the minimum value. And that way the minimum reward will be 0. All the other rewards will be positive. And it won't actually change the policy for each player, right? Like if we just add a constant to this, because this is a linear program, it won't change the point, which is the optimization point. Now it will change the value, right? But we can always recover the original value by adding the minimum back in, right? So we're going to get the actual policy won't be different, but we can easily recover the original value for that. So now, if we write it in this form, so first of all, so here I'm showing one of these, a game with 2 actions, and this is the solution where we solved it, you know, analytically. And we have, right, this is the optimal policy for player X, it's 0.75, and then the value for player X is this like negative 0.5. And this is showing a linear programming solution to this problem, where it looks like, you know, we have the same thing. Wait, actually, oh, sorry. Yeah, player X is 0.25. You're right, which means 0.25 probability for action 1 and 0.75 for action 2. Now here I'm just using, you know, one of the many linear programming solvers that you could use, but I'm defining, well, here I'm modifying the matrix here, but the constraints I'm writing down, these are just, because this is 2 actions, right? There are 2 constraint equations here, less than or equal to 1. And then the objective is to maximize the sum of x, where x and all the x's are positive. And then at the end, you can get the game value by inverting the sum of x, and the x policy will be, right, if we look at the change of variables, we can get back to policy values by just taking the game value and multiplying it by the V's that we have. So that's what's being done here. But now because we have a general linear program, we can actually write a function to solve a more general reward matrix, right? So here I have a matrix that can be any size, and I'm forming the constraints in a matrix form where this is I'm multiplying x by the reward matrix. This will form all the constraint equations. And then we can see as an example, this is the rock, paper, scissors game in the book where the 3 actions are rock, paper, and scissors. So we have for each player, whatever action you take, if your actions match, then it's a draw. And then there's one case where you lose and one case where you win. And that's just represented by this matrix. And then this is applying the linear solver to the rock, paper, scissors game. And we see the game value is 0, and the policy is uniformly random, which there's a note about this here. And the reason why the game value is 0 is because here you expect to win, lose, and draw an equal amount of times. But this is a game example where the Minimax solution, both players have a mixed policy. And this, I guess, right, I was showing these two player games where we can just make an arbitrary game. And this doesn't really represent anything you'd be familiar with. But the rock, paper, scissors game is a little less trivial, but it should be intuitively obvious to people that like the best you can do is to play randomly, right? Because like if you knew that the other player was selecting one of the moves more frequently than another, then you could always exploit that by selecting the move that does better than that, right? So the only policy that makes sense is a Minimax solution where neither player can actually come up with a better response to what the other one's doing, is to be uniformly random across all the actions. And we do see that solution here. And then, we can also make these arbitrarily large reward matrices. Here, I'm making one that's like binary. And we can just come up with, right, like use this to solve a problem. But it is not, I mean, this is like a highly optimized linear solver. It's, we can see like it's using this this is like a well-known linear solving program. And in order to solve the general problems like this, there are tons of tricks and things that people have figured out over years to find the solutions. And it's basically akin to what I did here, where I sort of went through these cases and figured out, which things I actually had to check. And all these different methods of linear solving look at the structure of the constraints, like what they actually look like, and then decide, what technique they want to use, how they want to iterate through the boundary space and find the solution. But, it's not something you're ever going to do by hand or even, a game with a pretty small number of actions. But, so like the point is, even to solve, these zero-sum normal form games for like non-repeated, just a single case for the solution, it does require this, solving this entire linear program, which, is pretty fast. Like this only takes a few milliseconds, but it's certainly much more involved than just, getting the reward value you would get for like a single agent RL problem. Now, what occurs here and then for the remainder of the chapter is looking at more complicated cases than the zero-sum game. The first of which is the general sum game, which introduces the Nash equilibrium. And again, kind of like the Minimax solution, the Nash equilibrium is defined as a policy where, a joint policy where every policy is a best response to the other policy. So kind of like what we said for the Minimax solution, except right here, we actually have to consider all of the I's, because in general, each agent can have a different reward function. Like they don't correspond to each other at all necessarily. But the point of the Nash equilibrium solution is that now you have n agents, multiple actions, and the rewards don't match. But there is still a joint policy for which, at the Nash equilibrium, no player can change their policy and gain an advantage from changing it. Of course, it's only a Nash equilibrium if that's true for every single player. Like you have to go and check all of the policies and all the, right, like all the possible responses, ways of modifying a policy against all the other fixed policies. And you shouldn't find for any agent a case where they can improve upon it. And Nash proved that there is at least one Nash equilibrium for all of these games. However, it's no longer unique. So we can have multiple Nash equilibria. And there is this comment here in the book. Let's see. Where does it say? Oh, yeah. So for non-repeated normal form games. So that's what we've been talking about, right? Non-repeated normal form. Pi prime can be computed efficiently using a linear program. However, notice that they don't actually put the linear program here like we have for this one. So I'm not sure. I'm actually not sure if the references, did anyone actually find this reference in the book or know where it is? Because I did try to check the book. There wasn't actually a section on footnotes. Like if you search for this in the book, you don't actually find this appears anywhere. There might be another part of the website where they had like additional footnotes. You can, oh wait, this appears. Okay, their names appear several times, but unfortunately there's no actual reference to the paper. So I don't think it will be the focus of this book to actually calculating the Nash equilibrium solution for general non-repeated games, or we'll focus on a solution type that doesn't use a linear program and will instead focus on these algorithms which are used for games with sequential moves. But we can at least see the concept of the Nash equilibrium here. So this is an example of, I think they mention it later in the chapter, but this is another game they wrote down. This is an example of a game where to illustrate different types of equilibria that are not the Nash equilibrium. But right here, they've written the reward matrix as one thing. Here, I've just split it up for the two different players. But this is not applying, a linear program or anything. What this is doing is showing for this game, this is the reward function for the X player, and this is the reward function for the Y player. And going through this is showing the best response that you could get for each player. So this is saying like if the Y player, for each policy that Y could consider here, this X is going to maximize its return from that. So what this yellow line is showing what X would select in the case where Y has chosen this policy. And similarly here, this is showing that for X, where for each policy X picks, it's showing the response that Y would choose to this X. And what you can see here is that there is this point, this transition point right here, where actually if Y selects this value of 1/3, then X is indifferent to that, right? It doesn't matter what X picks. This is a point where it'll have the same value everywhere. And similarly, if X selects 1/3, Y is indifferent to this. We can see it here in this way. Now, this plot is not an example as simple as before, where we can just find the maximization point here. Because remember, the Nash equilibrium is not just a point of maximum reward. It has to be a point where both players jointly can't improve their policy. But one way to see where the Nash equilibrium is the point where you make the other player indifferent to their action, right? I mean, this is a case where the Nash equilibrium is a mixed policy for both players. If it's actually not a mixed policy, then you don't get the same kind of solution. It's at an extreme point, like you see in the prisoner's dilemma. The Nash equilibrium is not it is not a mixed policy. It's just a policy where both players defect. But here we can see this point here is a Nash equilibrium because it is the point for both players where both players make the other player indifferent to the actions. And it's the only point in this space where that is true. So this is for the chicken. Where is it? This. Yeah, for this game. And there's a point here where we can see the Nash equilibrium occurs at a value of 4.66, which you can see here. It's this middle point here. And at both players' policy of 1/3, right? Which here we can see 1/3 here and 1/3 here. But what we'll get into later, at another session, is how for a general sum game, there are different types of equilibria that you can get that are not Nash equilibria, and this is one of the games used as an example of that. If I reset this, I think it'll create the prisoner's dilemma reward matrix. Yeah, so this is the prisoner's dilemma game. We can see in this case, the Nash equilibrium actually occurs over here. It happens to be a case where it's just extreme values the whole time, and both players defect. So x equals 0 means that you select the second action, which in the prisoner's dilemma is defection. So both players defect. Okay, so Victor, you did find the paper they're talking about, or is it a book?
I mean, at least there is a reference at the end of the book on page 341.
Oh, really? Then why couldn't... That's weird. How come when I searched for it, it didn't show up? Oh, 341? Oh, I see. Oh, because it didn't show up because the search term is different. There's actually another. Oh, it's just like not written the same way. Right? It's not this and this. It's okay. Well, that's pretty annoying that how they refer to it in the chapter doesn't actually match the footnote, but okay. So it's this one. Yeah, 2012. Okay. So yeah, I guess we can look at this to see what the linear program actually looks like for the Nash equilibrium case. But anyway, I think, yeah, so introduce the idea of the Nash equilibrium. So I think for next time, we will try to go through probably to the end of chapter 4 and just talk about the different types of equilibrium concepts for games and what the differences between them are without actually, solving them in this much detail. Because basically from this point on, the solutions become things that we can't just write down analytically. We have to use some of these other optimization techniques like linear programming. But does anyone have any other question about what we did today? Or...
Well, I have a comment that
okay, sure.
This reference does not actually solve for Nash equilibrium. It solves for best response policy for policies of the opponent. And you can use it to check if a given thing is a Nash equilibrium.
Okay,
not...
so all the work we did was solving a linear program which again gets pretty involved. All that can do is check if it's a Nash equilibrium. It won't
Yes,
actually even find it. So we're at the point now where we can just verify a solution. And actually, so these linear programming techniques, work in like polynomial time. I mean,
for zero
they-
time to player games.
yeah, like they've been yeah, I mean, for the linear program to verify the Nash equilibrium might run an even slower time. I don't know how elaborate it is.
No, to verify it can run in polynomial time, but
Okay,
then to
yeah.
find Nash equilibrium, it's probably exponential time. Like it talks
Yeah,
about this in the 4.11 complexity of computing equilibrium.
Yeah. So we'll get to that next time, but yeah, I mean, you can see, I mean, luckily other people have already figured out how to do all these linear program solutions. So it's nice we can just, pull them up whenever we need one. But there will be, I think, algorithms later or things you see for these multi-agent problems where each step of some iterative process might involve solving one of these programs to come up with a game equilibrium condition. So like you can have pretty involved like inner steps. And I think some of the moral techniques later are try to avoid some of those calculations. But because like when we go to the full problem, we're going to have a unique game for every step of the problem. So each game will have then a different, equilibrium solution for that the agents will have to consider. Yeah, and it comes. This Minimax solution is, again, like everything we've talked about here is about these joint policies, right? Minimax is also talked about in the case of two-player games where the players alternate, and that's very different because in that case you consider like the response of the other player only occurs like after you've made your move. So whereas in this case we're specifically considering responses that could be to an unknown policy that the other players made. So like again, like a joint policy is very different from where two players are alternating taking actions, and you have this like branching effect. Here we don't really have the same kind of branch. I mean, like this is much worse than a branching effect. I mean, we have to like simultaneously, right, optimize all of the policies, which could have, infinite, like when you talk about these alternating games like tic-tac-toe or something, the Minimax solution doesn't consider anything like a mixed policy because for those games, it's not actually relevant, right? You don't need to consider, whereas like you can see that for these games, right, for these like normal form games, like the game itself is deterministic, right? Like we know exactly what reward value we're going to get. We haven't even introduced stochastic rewards. But the optimal, like the equilibrium policy could still be a mixed policy between the two players. And that's because of the interaction between the two players that it ends up creating this stochastic reward situation because your reward depends on the actions of the other player. So just even introducing a single other player and the joint action already creates a lot of complexity to the problem. But yeah, thanks, Victor, for looking at that. I think, I did actually mention in the book that it's just a program for verifying the equilibrium. But I don't know. The book throws around a lot of stuff. And I think there's also a comment in the book about other books that go into more detail explaining game solution concepts. Oh yeah, for a more in-depth treatment of such questions, these books are recommended. Yeah, so I don't know. It might be worth at some point also looking at some of the material in these books because I don't know, at least I haven't read the book in a lot of detail later on, so I don't know how, like if it would be useful to have more background information for some of this stuff. I mean, I personally found that the treatment of the Minimax solution stuff in zero-sum games is a little bit glossed over, like the details of like what does this actually look like? And conceptually, it definitely is helpful to me to look at a simple like algebraic case and see what happens. But it may be that the book doesn't really go into it because this ends up not really being the focus of a lot of stuff later on in the book. But it's certainly important to understand this for understanding like game theory concepts and what types of solutions you could expect even in the case of what should be pretty simple games.
Yes, for multiple moves, if you have a zero-sum two-player game, then still you can solve it for every state using a linear program like that.
Mm-hmm.
I mean, you can't solve chess, of course, but that's because in games like chess, the size of the number, like the number of states is itself very large. Like here we are talking about polynomial complexity in the number of actions or in the number of state action pairs.
Yeah. Yeah, I guess. Oh, you're saying that you can still think of it as joint actions, even though it's sequential, because you just have.
No, I'm saying that you could
game.
recursively solve it. So if there is a finite game which ends in, say, 100 moves, then first you solve the last move, then you solve the previous one, and so on from the end. And each step of that procedure is this linear program.
Yeah, that's true. Although I think in the case of a game like tic-tac-toe, but in a game like tic-tac-toe, you don't get like the joint reward doesn't matter until the very end, which actually makes a lot more of the steps trivial. But like you don't have to worry about like stochastic like equilibria at the intermediate states, like mixed policies, because I mean, right? I mean, if you're talking about each individual step, like as the game state changes, right? Each like set of two actions, and you have sort of a new normal game repeated. But the reward matrix of that game is going to be trivial at each step.
So for the last step, until this is just normal form game, right?
Yeah.
Non-repeated. So you solve it for the last step, and then you back up your reward to the previous step. And now there it's again the normal form game and so on.
Oh, but the reward matrix is derived from the backup.
Yes.
From the anything. Okay. Yeah. So yeah, there is a way of doing that. I mean, you can also solve, tic-tac-toe or those types of with what is effectively a Minimax solution without even looking at the linear program. Like I've done it. Like I've definitely done it before where like you don't actually have to ever write down a linear program, at least like and like run a linear program solver.
That's correct, but that's because the game structure is different. So that on each move, only a single player makes a move, and here on each move, both players make a move.
Yeah. So it's not. I think like the important thing about what we're showing here is the joint action nature of the Minimax solution. But so if you have a game where the players alternate moves, it does have a very different structure, and you can solve it. I mean, it still ends up being like a Minimax. Actually, if you look up like Minimax solutions for, I think oftentimes what is being shown is an alternating game where players alternate moves and you have this sort of this branching effect into different states. But right, that a game of that structure never has to address this type of linear program where you have the joint action constraint. And I think usually when people talk about solving those problems, the algorithm ends up looking quite like pretty. I mean, you end up basically looking at. I mean, you look at this thing, but it looks a little different because in that case, the reward isn't. You don't consider the two simultaneous actions.
Well, on each step, you just have one. Like on each step, one of the players doesn't move, so you only have a minimum or a maximum, right?
Yeah. And what makes this whole linear program where you end up with potentially mixed policy solutions is because of this simultaneous min and max. But at least, yeah, like when I've been presented with minimax type stuff in the past, it's been in that alternating case where, yeah, on each step, you only have one of these operators happening. And then it is pretty easy to explain in that case, like what the algorithm's doing. But in the sort of original, like, I guess, you know, when von Neumann wrote this and was proving the minimax theorem, it was for the joint policy case. And the joint policy case is the one where you end up with these mixed policy solutions. I mean, it doesn't have to be that way, but you can end up with, you basically just add a lot of complexity to what the solution can look like when you have, yeah, the joint min-max happening at the same time. But I guess both are sort of considered minimax policies or whatever. But for the purpose, at least, of this chapter in this book, when we talk about this, we're talking about a 2-agent game with a joint policy space rather than alternating actions. Also, to do a 2-player game like tic-tac-toe, that doesn't require any multi-agent techniques to solve it in terms of reinforcement learning, because you can just sort of consider on each step one player being optimized against whatever the current opponent policy is. And that's why it is brought up as an example even in the vanilla RL book, because it's something where you don't need to actually talk about these equilibrium solutions for that.
Well, in the single vanilla, like in Sutton Barto book, there is not a zero-sum game, right? Because you only care about the wins, not draws.
But you can do it. I mean, you can do all of it. Like you can set it up as a zero-sum game or a general sum game, and still solve it.
Well, the general sum game is more complex, right?
For tic-tac, I mean, but you can still solve it, I think, with the single agent technique with the same, with alternating on each step, alternating which value function is being optimized. Because you can do it like you could assign a different value to draws, for example, where like it's not zero sum. Or like a draw could be, you know, a positive value, a small positive value for both players. That makes it not zero sum. But, well, I don't know. We can look at it in more detail later. But I don't think you have to dip into any of these game solution concepts to solve it in that case. But maybe, yeah, because you still take it where each agent is trying to maximize its own. Well, I don't know. No, maybe you're right, because it's unclear what it means if you have, like, you may have non-unique solutions. I don't know. I'd have to try it. I mean, you can also always like fully optimize one player against the other and then alternate back and forth. And even if it's not zero sum, and that should arrive at a Nash equilibrium if you do that. If it's a general
so there are Nash equilibria and they are not unique because one of the players doesn't care what other wins or not. And for some moves, it doesn't care what the move it makes, but the other player depends on, like the other player's reward depends on.
Yeah, so if you set it up as an alternating learning process where each player just optimized against the other one fully, and you set it up where, let's say, it was like win was 1, loss was -1, and if, let's say, draw was 0.5 for both players, so then it's not zero sum because the draw condition is a positive sum. Then I guess if you do that process, it could either end up in one of the equilibria or it could start alternating between them as you you do the training back and forth. I don't know, you have to try it out. But yeah, and that's a case where you don't necessarily know which equilibria it's going to end up in ahead of time, because it depends on like the initialization. Yeah, if the equilibrium is not unique, I guess in that case, the Nash, there would be more than one.
Well, if
Nash
the
equilibrium.
score for a draw is something in between the loss and the win, then max min is the same as min max effectively. So you end up in a game which always ends in a draw. But if one player doesn't
we're
care
both-
if it loses or draws, then it becomes a different game.
And the other player does.
Yeah, one player cares whether he wins or not, but another
Yeah,
player
you
doesn't
mean
care
yeah.
whether it draws or loses.
Yeah, like if both players had the same reward for a draw that was like positive but less than 1, it still would create a preference the win. And yeah, I mean, draw is still preferred to loss anyway, even in the zero-sum case. Yeah. So I see. Well, yeah. So there's like ways to formulate the game where, yeah, you have non-unique equilibria. And really, selecting between the equilibria is really, I think, a lot of the focus of this book, and multi-agent learning in general is defining like which equilibrium we actually care about, and how do we create an algorithm that produces the equilibrium we care about. At least from what I've read so far, that's my understanding. So yeah, thanks for the discussion. Is there anything else before we close? And does that sound good for next time to try to just finish chapter 4?